Okay, I think chords of progress. All right. Okay, anyway, an arithmetic sequence. It's a very basic sequence. So you guys already got exposed to sequences right before left for break, right? And oh, juniors, congratulations. That was great. So that's awesome.
Were you surprised? Or
No, not at all. You guys had a good leader. So congratulations. Oh yeah, okay, you too. All right, I was looking at Andre. I don't know. All right, okay. Yeah. All right. Anyhow, so we looked at sequences in general before we left for break. Now we're gonna look at very specific sequences. So the first one we'll talk about is an arithmetic sequence. Very basic, just has a common difference. Meaning you're gonna be adding or subtracting the same number over and over again. Generally, we'll say we're adding because you could add a negative number and still the same effect of subtracting, right? Like here, 1, 4, 7, 10, and so forth. What's the pattern for that one? Plus 3, right? Not that hard. So and today we're just going to talk about sequences. Sequences is simply about listing the numbers. Not this week, but next week we'll talk about a series when you add up numbers in this pattern. We'll talk about that later. That's actually where things can get really messy and complicated. We're going to keep things pretty basic today. But there are some homework problems that are a little crazy, and I'll show you that in a moment, or in a half hour. So example 1. They asked you to write out the first 3 terms of each arithmetic sequence to state the common difference. And by the way, when we say terms are just the numbers in the pattern. So the first term's the first number, the second term is the second number, third term is, and so forth. Sometimes we generally call it the nth term. So when you see a sub n, you see n as a subscript. I call this the nth term. So you can choose what you want n to be. Like, let's say I want to find the 100th term. And guess what? Plug in 100. You get the 100th term. So it just gives you the formula directly. In fact, actually, we call these explicit. We call this an explicit formula. Just in general, what does explicit mean? Direct, right? Like if you listen to something that has explicit lyrics, you know, it's very direct, right? So it's kind of the same thing. It just gets you the answer directly. And the difference will always be the same between consecutive terms. So each of these are explicit formulas. Each of these are. They're all arithmetic, but they're all explicit. So if you're asked to write the first 3 terms, I want A1, A2, and A3. We always, oh yeah, another thing I need to state as well. You always start, thank you for bringing that, Rihan. Start with n equals 1. Yeah. Start with n equals 1, and n will always be.
I'm just showing it all. I'm sorry.
Yeah, n's always a positive integer, by the way. Oh, let me erase the board. Sorry about that.
My speech.
So you're going to go increments of 1. So you go 1, 2, 3, 4, 5, and so forth. So, Olivia, you have a question? Exactly. Right. So there will be no y-intercept. You start, and it's actually discrete, meaning you're not going to connect those dots either. So you like actually you could graph this in the graphing calculator. Well, you were mentioning that about regression, right, William?
Yeah.
Yeah. Okay. So I could show you later on how it looks, but anyhow, if I plug in 1, what do you get? Plug in 2, what do you get? Plug in 3, what do you get? And what's your common difference? And notice that the coefficient of n represents common difference. Okay, let's look at part B. No, we never make a negative. No. For sequences, the first term, you can't have the negative 5th term. Like, what would be the net? Like, put it this way: like, if I were to give you a very specific, real life example, like, say the actually great example. We'll do this next week. It's a great problem to do. Let's say the seats in Harmon fall into a pattern. You don't have the negative 5th row. You have the first row, the second row, the third row, 4th row. So it's like that. Okay, what's A1 here, guys?
2.
A2
-3.
and A3. So clearly my common difference is -5. Good. Okay. Now, there is a general formula you can use for arithmetic sequences. If you think about it, you're adding D over and over and over and over and over again. For example, A3, wouldn't that be the first term plus the common difference twice? Wouldn't the fourth term be the first term and adding the common difference 3 times? So one way you can think about is like, here's A1, here's A2, here's A3, here's A4. Once I know the first term, how many times do I have to keep jumping to get to A4? 3 times. So ultimately, we could come up with the general formula for an arithmetic sequence. How do you think I'd write the general formula for this?
N minus 1 times common difference.
Yep, there you go. Nice. Excellent. So it's not something that just fell out of the sky. There's actually a rhyme and reason to it. Actually, I really love these kind of formulas because they're very logical. You have the first term plus 1 less than n times the common difference. So if I want like the 100th term, I wouldn't add the common difference 100 times. I would add it 99 times after the first term, right?
Why do we not do like a of 0?
No, we don't.
Bro, wouldn't it be a lot easier to just write like a of 0 plus n?
We just don't do that. Yeah. So sorry to disappoint you. Or I'm not sure that's disappointing. So the nth term again is going to be A1 plus n minus 1 times d. That's all. So now you're asked to find a formula for the nth term of an infinite. Okay, infinite means it never ends, right? It goes on forever.
It's nuts.
Whose common difference is 3 and first term is 2. So we're at the first 3 terms. Well, it's pretty obvious. The first term is 2. What comes after that? If common difference is 3, 5. So your formula would be an equals 2 plus n minus 1 times 3. And you can leave your answer like that. You don't have to simplify it. If you want to simplify it, go ahead. If you simplify, you should get what? 3n minus 1. Right? Does that make sense?
Yeah.
Yeah. Okay, all's good? Okay, pretty straightforward. But they do get crazy. Just wait. All right, let's look at example 3. For example 3, the 4th term is 20, the 13th term is 65. Write the first 13 terms of the sequence. Okay. Well, here's what I would do. You could get fancy with the formulas or use logic. I prefer to use logic. So I'm going to make these little slots for the first 3 terms. And what's my 4th term again? 20. Then 5, 6, 7, 8, 9, 10, 11, 12, 13. My 13th term is 65. How many times do I have to jump from the 4th term to the 13th term? How many times do I have to apply the common difference? 9 times, because the difference, right? Difference between 13 and 4 is 9. So essentially what you could do, if you so desire, you could try to think about it intuitively. Okay, well, how many times? How do I do that? Right? You can do guess and check, but really, let's just be logical about it. What if I did 65 minus 20 divided by 9? Yeah. What's that going to be?
5.
Got it. There we go. So the common difference is 5. Now I could write out all the terms, right? 25, 30. I know it's very cumbersome, but we're just doing it just so you guys get the idea. 55. That's terrible looking 55. Going backwards.
How would you use the formula?
What you would do, if you want to be incredibly formulaic about it, you would say an equals a1 plus n minus 1 times d. So what a student could do is say, well, I know a4 is 20. So then you have 20 equals a1 plus 3d. And then you have 65 equals a1 plus 12d, I think. And then you substitute them afterwards. Some people who I don't know, They just have a phobia with intuition, if you want to call it. I don't know, or a phobia about logic. They just want that comfort of like using a formula. You could, but I will say it's going to be in your best interest to really think about these logically. Occasionally, the formulas can come in handy. You'll see when we get to some problems later on. But yeah, using logic is totally fine. Okay. Did example 3 make sense? Okay, a couple more, and then we're going to move on to geometric. Okay. Find the 20th term of the arithmetic sequence whose first two terms are 2 and 9. Okay. Well, the first term is 2, the second term is 9, and then dot, dot, dot. We want the 20th term, guys. What's the common difference here?
7.
And you know it's going to be consistent because you're told that. How many times do I have to apply the difference of 7 after the first term to get to the 19th term? Sorry, to the 20th term. I said the answer. 19 times. Or you can start the second term and add the 18 times. It's up to you. Totally up to you. So you can do 2 plus 19 times 7, which I think is 135.
Yeah.
Am I correct? Yeah, 135. Okay. Okay, let me talk about example 5 because that's kind of funny. And then we'll move on to B. Geometric sequences. Okay. Now this one's a little funny. This is what we call, we don't really do too much with this. And actually, I spoke to Ms. York about this. She's not really big on this stuff. Because it's not really a big part of BC calculus, but it's called recursive. Now, we hear the word recursive. It sounds like recurring. What does it mean if something's recurring? It's repeating, right? Now, the way this works, it's a little funny, but let's start with k equals 1 to get this kick-started. If you k equals 1, wouldn't that be a2 equals a1 minus 2? What's a1? Were you told what a1 was? Okay. So you work out, what do you get? Great. Now let's find the next term. This is not a fun process, and you'll see why in a moment. So now you plug 2 in. What's a2? Because didn't you have to use the previous one? That's why it's called recurring. You use the previous one to get the next one. What's that going to be? Okay.
Can't you just like only do the first one and then see that
What's the pattern?
Don't you just know that
something's in the arithmetic sequence that's just -2 every time?
-2. So if you want to write the first 5 terms, it's pretty obvious. That's 3, 1, -1.
-3,
Right. But sometimes you might be given a formula that doesn't follow an arithmetic pattern.
Yeah.
So yeah, right. But here's the thing. What if you didn't know, you couldn't recognize the pattern, right? And ask you to find the 1000th term, then a direct form would be better, right? That's why it's called explicit, the forms that we've been doing already, because it's direct. So explicit is going to be the better way. But
Wait, what's the explicit one?
well, this right here, an equals a1,
Plus the -1.
because it gets you the answer. It gets you whatever term you want directly.
What's the other formula?
This way. Oh, the recursive.
Oh,
No, this is all under the umbrella of arithmetic. We haven't gone to geometric yet. We'll get to geometric in a moment. So what's the nth term? How do I find that? Well, that would just be an equals, what's the first term? 3 plus n minus 1 times -2, right? So you should get -2n plus 5. So that's your explicit. That's your common difference, first 5 terms. Yeah, Ron, go ahead.
Can you express any like arithmetic sequence with like a sub k plus 1
Correct.
equals a sub k plus d, and then give them a sub k?
Sure. Yeah, you can always express it as a recursive, right? But we don't really spend too much time with that. So, all right, we're good on that. All right, cool. All right. Okay, now let's move on to geometric. Now, geometric is when you're multiplying by the same number over and over again. There's a common ratio, not a common difference. So like 2, 6, 18, 54. What's the pattern there? Multiplying by 3, right? 2, 6, 18, 54. You multiply by the same number is the same thing as dividing. You just divide by its reciprocal, right? Same thing. If you multiply by 3, that's the same as dividing by 1/3. Multiply by half is dividing by 2. Same thing, right? So when you see this here, if you take two consecutive terms, a sub n plus 1, that'll always be a consistent ratio. Okay. So let's determine if these are geometric. And if they are, let's see what R is. Okay. So is there a common ratio for part A?
Yeah.
There is?
I don't know.
No.
There's 2n.
This is arithmetic, right?
Okay.
Or arithmetic, if you want to kind of call it that. Yeah, how about part B?
Which was 2.
And R is 2. So you can see how these are exponential in nature, the geometric. What about for C? Was R equal? Good. Perfect. Notice how the signs alternate and numbers get tinier. We're going to talk about that in just a little bit. Because that's kind of a special situation. And by the way, notice we have ... afterwards. So these are infinite sequences. These do move on forever. We're not ending it, so we're just letting them go. Okay. Now, how can we come up with the nth term? Well, essentially multiply by the same number over and over again. If you think about it, A1 equals A1, right?
Yep.
Well, duh. What would A2 equal? A1 times R. What would A3 equal? Times R squared. What would A4 equal? So can I come up with a general formula? Good. Yep, you got it. Good work. Yep. Make sure my R's and N's don't blend in. So A1 times R raised to n minus 1 power. Okay, pretty straightforward, right? Now write the first 4 terms of the geometric sequence. This first term is -1. Common ratio is -2. Okay, that's easy. -1, 2, -4, 8, right? So A sub n. We're good on that? Look how bright this is. So nice. Okay. All right. Let's keep moving. Let's do a couple more here. Then we'll talk about an infinite geometric series. I'll talk about that for a little bit, and then you guys can just work on homework.
So do you like the new projector?
I love it.
It's
Awesome.
actually crazy bright. It's like not even.
It's way better.
And they even gave me like a new remote too. Like, yeah. A little large. Was that? Yeah, over break they replaced all of them. These are the ones that they have, I think, in the main building. I think the second or third floor. Yeah. Yeah. All right. So what's the common ratio, guys?
3.
Now, if I want the 9th term, so this is explicit again. Take your first term and multiply by 3 raised to what power?
8.
8, right? Because you got to multiply R 8 times. And please, 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 I don't think you guys do this. Please don't do this. Do not multiply 5 by 3 first. Please don't do that. PEMDAS, you guys know better. And let me get a calculator.
32,805.
Pretty big. You need to tape your glasses, dude? You're good, Easton?
Yeah.
All right.
Are they still broken?
Yeah, I had a backup on my, I couldn't find it.
Did you sleep on them or did you sit on them?
I slept on.
Were you sleep with your glasses on?
No, oh, it's my thing.
Okay, guys. All right. Let's keep moving. All right. Okay. We don't know about sleep patterns. All right. We're talking about patterns. Okay. Example 9. Yes, Easton, go ahead.
So, like, what's the pattern of today?
Yeah, exactly. Because I'm still kind of like, I do have the packet actually ready for Friday. Oh, by the way, I won't be here Friday. Ms. York will teach you guys. She's very excited to teach you guys. So she'll actually, but I have the materials ready to go. If you guys want them, I could hand them to you. But I think I'll just wait.
You just post them.
I'll post them. Yeah. Okay, example 9. Fourth term geometric sequence 125. Okay, so 1, 2, 3, 4. And I'll do dot, dot, dot. I don't feel like writing a whole bunch of these. Then dot, dot, dot. So that's the 4th term. That's the 10th term. I want the 14th term. Okay, how many times do I have to multiply R to the 4th term to get to the 10th term?
Fine.
6 times, good. So 125 times R raised to the 6th power. Does that make sense? Because you have to apply the common ratio. So I didn't use any fancy formula. So now if you really want it, I'm shooting it on the board because I don't really want to write this out. But so Rion, you're asking like, well, other ways we do this, right? But you could say A10 equals A1 times R raised to the 9th power. So that'd be 125 over 64. And then you can also say 125 equals A1 times R cubed. Then you can do substitution and compare those. You could do that if you want, but I just rather use logic. So what does R6 equal, guys? Make this true. And 64 is a perfect 6th root. Actually, there's gotta be careful here. What's really the answer for this one? Is it 1/2?
Oh.
Could be positive or negative. Now it won't matter because we're looking for an even number term. But if I ask for the 13th term, I could trick you that way.
Why?
Because I want to.
Yes.
So I want to do that to you. So anyway, be mindful about that.
So we should always assume
If you're even rooting, yes.
But
Yes.
we know in this case that it's gonna be positive.
Right, because it's the even term, right? So if I work it out, there'll be 125. And I have to multiply 1/2 to what power? Correct. And that should be what's that? 64 times 16, 1024. So it's 125 out of 1024.
Whenever you get plus minus, like
He didn't know.
Bless you. Okay. Does that make sense? We're okay with that? All right. Now, let's explore. Actually, questions so far? No? Okay, we're at the home stretch. We get what time today? 35. Okay, good. Yeah, I'm almost done here. And I think I'm going to reduce your homework a bit more. Now, the more I think about it. Yeah, kind of crazy. All right, so
get sick of it on the first day.
yeah, I know, right? Okay, so let's explore example 9 a bit more, right? Can we find the sum of all terms in that sequence if we let the sequence progress forever, meaning we have an infinite number of terms? So, for example, I'll do this off to the side. So the 4th term was 125, right? What would have been the term right before it? 250, right? Because we're multiplying by 1/2. The one that we just had. Let me go back. Let me go back up here. I need some space. So wasn't 125 my 4th term? What was my 3rd term? What was my 2nd term? What was my 1st term? And then it kept dropping, right? Ultimately, if you go on forever, if you go out towards infinity, that's gonna be a super small number, right? Because you multiply by 1/2 repeatedly, right?
You're saying as n approaches infinity?
Yes, as n approaches infinity. Actually, that's a great way of writing it. And you know what? I should have said that because we're talking about calculus now, right? So there's going to be so Ms. York is actually going to teach you more the calculus element of it on Friday. As n approaches infinity, right? What's a sub n going to approach?
Zero.
It's going to approach 0, right? as n approaches infinity, right? A sub n is going to approach 0. So you actually could find the sum of all these numbers. It is possible. As long as the ratio, the absolute value of the ratio is between, sorry, the absolute value of the ratio is less than 1. What that means is that R is between -1 and 1, non-inclusive. Because if R is 1, then guess what? You're just multiplying by 1 over and over again. Like if R is 1 here, right? That one next to a bunch of thousands, and that sum would be infinity. I don't know. If I were to add up all the terms, just go forever, right? But what's going to happen?
Because when it's in between those, it's just approaching 0.
Right. So here, let's talk about the formula. The sum's going to be this, and that's something we're going to spend a lot of time talking about next week. The sum of an infinite geometric series. Now, a series, the difference between a series and a sequence is simply a list of numbers, just so you know. Just so we don't get our terms confused. So when I say sequence, that's exactly what I mean. Just a list of numbers. Like you guys take bio, you talk about DNA sequence, just a bunch of letters, right? Just a list of numbers, that's all it is, right? A series is a sum. Now I'll tell you what the formula is right now. It's gonna be that A1 over 1 minus R.
Really? Does it?
Here's the reason why. It's not, unfortunately.
Well, yeah, it keeps going up.
It keeps going up, keeps going down,
Yeah.
right? Because you're adding. Okay, you have this, right? Oh, sorry, I meant to put A2. My apologies. So if you add all these up, right? Wouldn't it look like this? I'll do some red so it stands out. The first term's A1. The second term's A1 times R. The next term's A1 times R squared. The next term's A1 times R cubed. Plus dot, dot, dot. A1 times R raised to n minus 1 power. You would agree with that, right? If you add up all the terms in a geometric pattern, it would look like that. Can I factor something out?
A1.
A1, very good. So if you factor A1, what are you stuck with? 1 R plus R squared plus R cubed plus dot, dot, dot R raised to n minus 1 power. Now, this is the part where I need to think a little more about this. Well, because I do need to derive the geometric series form, which I'll do for you guys next week. But if you go through, if you assume R is between -1 and 1, non-inclusive, ultimately all this junk over here, I do need to think about the derivation. That's my fault. I didn't prepare for you guys, so I apologize about that. So yes, Clay, I do a better job.
The second class.
Yeah, I do better. Yeah, you guys got kind of screwed over. Sorry about that. But all this becomes 1 over 1 minus R. That's what it actually adds up to. Just have faith that that's what happens.
I guess.
Yeah, just believe me. Okay. That's what happens if R is between -1 and 1. Yeah, I just have to look at the derivation of a geometric series, but it's all good. So ultimately that becomes this. A1 times 1 over 1 minus R, or A1 over 1 minus R. So it'll just converge. And this is the concept of convergence. So for example, when I had 2, 6, you don't have to write this down, 54, that won't converge. We would say this diverges because numbers just keep getting larger, right? So sum keeps getting larger. But what happens when we have 1000s, 500s, and so forth, right? Ultimately, what does the sequence converge to? 0. So the sum would also converge to a certain number. And that's gonna be a big concept when you move on to BC next year. Let's just do a couple problems here, then we'll be done for today. Okay, now I don't know if you guys have seen this notation, and we'll talk about it next week. Oh, so you do know what it is?
I
Have you
don't
seen this before?
Sigma is-
A little bit.
I mean, I
Okay.
think I can get to understand it.
So this is called
I think
sigma
we did
notation.
And approaches infinity.
Okay, if you have any siblings who are in a fraternity or sorority, they probably might have seen this. So the capital E is a Greek alphabet. It's called sigma. Here's how it works. This is how you start. This is how you end, which obviously you never end. It's infinity.
It's always bigger.
No, you can have a number there. And that's going to be your formula you're going to use. Now, by its nature, this is exponential, right?
Correct.
Exponential are geometric sequences because you're multiplying over and over and over again. So if you think about it, when n equals 0, now I know sometimes we let n, I know we're letting n be 1 for sequences, but for sigma notation, you could actually start however you want. And it's always going to be a whole number, or sorry, I take it back. It could be an integer, but you go up in increments of 1. So if I plug in n equals 0, what does the formula tell me? It equals 1. Good. So that's your first term. And the sigma notation means sum. You're going to sum up all the terms. For example, if n equals 1, what will be my next term if n equals 1? N equals 2, what's my next term? 0.16 and so forth, right? Notice that numbers are getting smaller and smaller, they're getting tinier. So ultimately, the sum of all these terms would converge. So if I want to do this, I'll just use this formula. Because isn't my R between A1 and 1? What's my R value? So you just do 1 over 1 minus 0.4, which will be 1 over 0.6.
Why do you do one?
5.
Because we were told to start n equals 0.
Oh,
That's why. 0.6 is 3/5 as a
5/3.
decimal, so it's 5/3. So believe it or not, all these numbers here would add up to 5/3. If I were to add all this up.
I believe it.
You don't believe it? Okay,
Prove it.
I will prove it. Here we go.
Point of the answer.
What was that?
Point of the answer.
No, I'm pulling the calculator.
Oh,
So I'm gonna show you can look at the calculator. Here we go. Clear for moments. Okay, if you hit alpha window, remember I told you where n deriv was? Absolute value, log. By the way, the fourth option, fn int, is integrals. You'll do that in the fall. We don't do it in this class. That's the second portion of calculus. So if you pick this one and use x, you don't have to use n, x equals 0. Now, if it's infinity, make it a large number. Let's say we make it like 50. Don't make it too large because the calculator will take too long. And what's the formula? 0.4 raised to the x power. There we go. I mean, if you try math frac, it's because it's an approximation. It's not, oh, it does give me 5/3. Okay. Just be careful. Because if I like do this like to like 1,000th, 50 is a good enough approximation.
Is it actually like doing the sum?
Oh yeah.
oh boy.
Take a little break.
Do you think that it's like?
He'll get it.
it'll be
Or it might give an error. Because it's just too make. I'm making it think too hard. But it's trying to do 1,000 calculations. Oh, it did do it. Okay. But see, it took a little while, right? Don't do 10,000 or 100,000. It's crazy. Don't do that. And again, alpha window is where you can locate it. Or if you hit math, if you can go down to summation. Yeah, summation does the same thing.
Yeah.
Yeah, there's a bunch of other stuff there too. So anyhow,
That's good.
so let's look at part B. What's the first term, guys?
-1. Wait, no. -2.
Yeah, -2, good. And what's your R value? We're multiply by over and over and over again.
0.2.
Good. It's -2 or 0.8. 0.8 knows 4/5. Is that right? She get -5/2, right? Yep. Okay.
Oh.
Okay, last one, number 11. Find the rational number representation of 0.1 repeating. So it goes on forever. Okay, rational number means we want to find it as a fraction. I mean, we know it's 1/9. Hopefully you guys know that, right? Yeah, I mean, that's pretty obvious. But how can we think of this as a geometric sequence? That's a trick. 0.1. Well, actually, we do plus signs because we're adding up. 0.01 plus 0.001. Would you guys agree with what I'm doing right now?
Yeah.
Right. Okay. So what's your A1? 1. What's your R? 110. 4.1. Same thing. Oh, I'm sorry. Gosh, I was like nearly perfect today. Thank you. So if I work that out, so 0.1 or 9/10. So it's 0.1 times 10/9.
Yeah.
And isn't 0.1 1/10? Is that kind of neat?
Just 1/9.
So that's how you can prove it's 1/9. Using the lens of a geometric series, but infinite with a ratio between -1 and 1. So. Okay, homework will be this. Let's get a head start, guys.
Let's take a peek at how many problems we got.
Yeah, I know.
Before
hold
we
on.
Just start doing it.
I do need to hold on, see here. Where the heck is it? Okay, I handed out the I need. Oh, I did scan it. Hold on, I did scan it. I did this morning. Here we go. Okay, ooh, that's a good one. Here we go. Okay, I'm going to
Come on.
do you guys a solid. Instead of odds, every other odd. Okay, so every other odd. 1, 5, 9. Is that what kind of pattern is that?
Something.
What's for?
Arithmetic.
Or actually, I should say use a following formula. Use this formula to no. Okay.
And we're doing the entire packet.
Times 4. Good. Okay. So you're gonna do so this packet here is the nuts and bolts. It's very basic, fundamental, foundational arithmetic geometric series stuff. There's 3 sets. One's arithmetic, one's geometric, and the other one's infinite geometric series.
We're doing the whole packet.
Every other odd.
Just this one homework assignment.
Yeah. What's wrong with that?
Let's see the odd.
Every other odd. I said, yeah. You guys can do it. Well, yes, I'll put it right now. Okay, and then hold on.
Yeah, take a minute.
You guys can knock this out, I think, in the next 20 minutes. But my hope is you guys can knock out most of it. Every other odd. Okay.
And then we'll do every other even.
And then
And then every even.
these are the tough problems.
Wait till we do the those.
I want you to find these. Yeah. Just 1, 2, 3, 4.
Maybe do 1, 2, 3, 4.
Yeah. These are the tough ones. So I think someone's asking, is this a tough unit? Yes, it is. This is probably the toughest unit we have all year. But this is the whole point. I want you guys to get. So we're gonna revisit this.
Gotta
next
remember,
week.
gotta remember to show my work this.
Okay, this is.
Yeah.
Like this all like.
Every other odd. Other odd. 5, 9, 13, 17, 21, 25.
Every four.
Yeah. Exactly. Okay.
So we're gonna do this back and forth, like, we're gonna do every other odd.
No.
Two?
Just
Okay.
just to have extra problems we can do for later. So and then the other packet I gave you guys, 1, 2, 1, 2, 3, 4. I'll put the homework in Schoology.
What is that? Wait, wait, wait.
The hard ones. And by the way, the answers are included in the packet, just so you know. That's what's a little thick.